100,000 years ago, Earth was in the grip of a profound transformation. Ice sheets kilometers thick advanced across continents like slow-moving crystalline tsunamis, reshaping landscapes and rewriting the story of life on our planet. Imagine standing at the edge of an ice sheet stretching beyond the horizon. The air is bitingly cold, each breath visible as delicate clouds of vapor. The world before you is an expanse of pristine white, reflecting sunlight with blinding intensity. This was not a peaceful time in Earth's history. It was a period of extreme climate volatility that, by all reasonable scientific expectations, should have disrupted the delicate balance required for complex life to thrive. Yet here we are. The paradox that brings us to this story is deceptively simple. How did Earth maintain conditions suitable for complex life through cycles of climate change so extreme they transformed entire continents? More importantly, why didn't these cycles spiral out of control? You see, our planet's climate system isn't like a thermostat with a single setting. It's more like an intricate symphony of interconnected systems that somehow maintained a habitable range despite enormous external forces pushing it toward extremes. The Ice Age cycle is driven by subtle variations in Earth's orbit and axial tilt. These Milankovitch cycles, as they're called, produce only minor changes in solar energy distribution. Yet they trigger climate swings far larger than these initial nudges would suggest. This amplification is what puzzles scientists. Small orbital changes shouldn't create such dramatic climate shifts. It's like pushing a child on a swing and watching them suddenly launch into the stratosphere. Something doesn't add up. And here's where our mystery deepens. The climate record shows these Ice Age cycles have repeated roughly every 100,000 years for the past million years. Before that, they followed a different rhythm, occurring every 41,000 years. Why did Earth's climate pulse change? And more importantly, how did life persist through these dramatic transitions? The survival of complex life through these cycles wasn't guaranteed. In fact, it may have been highly improbable. Our journey tonight explores what geologists call the 100,000-year problem, a fundamental mystery about Earth's climate system that challenges our understanding of planetary stability and the resilience of life. We'll examine ice cores drilled from ancient glaciers, sediments from the ocean floor, and fossil records that reveal how life responded to these massive climate transitions. Each offers clues to how Earth maintained its habitability. The stakes are not merely academic. As we face human-induced climate change, understanding how Earth's natural climate system responds to perturbations becomes essential knowledge for our future. Tonight, we'll explore ideas from mainstream climate science while venturing into more speculative territory. We'll distinguish between what we know with confidence and what remains theoretical, always marking the boundaries between established science and exploration. The Ice Ages represent Earth's great survival story, a testament to the resilience of our planet's systems and the life they support. Yet they also reveal a troubling vulnerability in the machinery that maintains our habitable world. By some scientific measures, Earth shouldn't have survived these cycles intact. The feedback mechanisms that amplify small orbital changes into massive climate swings should have pushed our planet into permanent states of either ice or heat. Instead, Earth found balance, oscillating between glacial and interglacial periods in a rhythm that somehow avoided catastrophe. This balance may have been precarious, perhaps even lucky, raising profound questions about planetary climate stability. As you settle in for this exploration, picture yourself traveling backward through time. The modern world recedes. Cities vanish. Forests expand and contract across continents. Ice advances and retreats like a breathing entity spanning millennia. We're about to witness Earth's great climate dance, a complex interplay of astronomy, geology, biology, and atmosphere that created the conditions for our existence against seemingly impossible odds. This is the story of Earth's survival through the Ice Age cycle, a mystery written in ice and stone, waiting to be deciphered. It's a tale of delicate balance and resilience that challenges our understanding of what makes a planet habitable. Welcome to a journey through Earth's most extreme climate transitions and the surprising story of why we're still here to tell the tale. Chapter 2: The Pendulum of Planetary Fate. Why should this ancient climate mystery matter to us now? Because we live on a planet that contains the very same systems that produced these dramatic swings. Earth's climate machinery hasn't fundamentally changed, even if we are now the dominant force affecting it. Understanding the Ice Age cycle is about more than satisfying scientific curiosity. It's about comprehending the full range of behaviors our planet's climate system is capable of expressing, including potential tipping points and abrupt transitions that could affect our future. When we examine ice cores from Greenland and Antarctica, we discover something alarming. These ancient archives reveal that Earth's climate can shift dramatically not just over millennia, but sometimes within decades. Temperatures in some regions changed by up to 15 degrees Celsius. These rapid transitions, called Dansgaard-Oeschger events, happen repeatedly during the last glacial period. They represent climate shifts so abrupt that if they occurred today, human civilization would face unprecedented challenges within a single generation. What triggered these rapid swings? And what prevented them from becoming runaway processes that rendered Earth uninhabitable? These questions strike at the heart of our understanding of planetary stability. The stakes become clearer when we consider that our modern civilization developed entirely within the Holocene, an unusually stable interglacial period lasting roughly 11,700 years. Our agriculture, cities, and infrastructure all evolved during this climate calm. Yet this stability appears to be the exception, not the rule, in Earth's recent climate history. The Ice Age cycles reveal a planet prone to dramatic oscillations, with stability as only a temporary state between transitions. If Earth had followed a different trajectory during any of these climate transitions, if certain feedback loops had amplified just slightly more, our planet might have experienced a runaway icehouse or greenhouse state, potentially incompatible with complex life. This raises profound questions about planetary habitability throughout the universe. If maintaining the narrow temperature range required for liquid water and complex life depends on such precarious balancing acts, perhaps habitable worlds are far rarer than we've assumed. Consider what would change if we discovered that Earth's climate stability was highly improbable, perhaps even requiring a series of fortunate accidents in our planetary development. Such a finding would dramatically alter our estimates of potentially life-bearing worlds. The implications extend to our search for extraterrestrial intelligence. If complex life requires not just the right initial conditions, but also stable climate systems over billions of years, the number of worlds hosting technological civilizations might be vanishingly small. For our own future, understanding the Ice Age machinery offers crucial insights into climate resilience. What natural mechanisms helped Earth recover from extreme states? Could we learn from these processes to address our current climate crisis? The specter of abrupt climate change also looms large in our investigation. If Earth's climate has natural thresholds beyond which rapid transitions occur, we need to know where these boundaries lie and how close human activities might be pushing us toward them. Perhaps most importantly, the Ice Age cycles reveal a fundamental truth about Earth. Our planet is not a passive backdrop for human activity, but an active system with its own complex dynamics and thresholds. The scientific quest to understand these cycles has produced stunning discoveries about Earth's history. We've learned that atmospheric carbon dioxide levels and global temperatures have moved in lockstep through these cycles, revealing their intricate relationship. We've discovered that the deep ocean currents, Earth's global heat distribution system, have shut down and restarted multiple times, triggering cascades of climate effects across continents. These ocean circulation changes may have been key drivers of abrupt climate events. The ice ages have also revealed Earth's interconnectedness. Changes in one region propagated globally through atmospheric and oceanic teleconnections. Northern Hemisphere ice sheets affected monsoon systems in Africa and Asia, creating climate ripples worldwide. For life on Earth, these climate oscillations drove waves of adaptation, migration, and extinction. Species either adapted to changing conditions, moved to more suitable habitats, or disappeared. Yet remarkably, biodiversity as a whole persisted and even flourished. Our own species emerged during this time of climate volatility. Homo sapiens evolved in Africa around 300,000 years ago, during one of these glacial-interglacial transitions. Our earliest migrations occurred against the backdrop of a highly variable climate. Could this climate variability have been a driving force in human evolution? Some scientists propose that adapting to rapidly changing environments selected for bigger brains, complex social structures, and technological innovation, the very traits that define our species. This perspective transforms our view of climate change from purely a threat to a complex evolutionary force. It suggests that environmental variability, within certain bounds, might have been essential to the emergence of human intelligence. Yet there's a critical distinction between natural climate variations and current human-induced changes. Today's warming is occurring at rates potentially 10 to 100 times faster than most natural transitions, outpacing evolutionary adaptation for many species. As we unravel the Ice Age mystery, we're also gaining perspective on humanity's place in Earth's story. We are both products of this dynamic planetary system, and now its most significant influencers, a species with the power to affect global cycles. This investigation into Earth's glacial rhythms thus becomes a mirror reflecting our own relationship with our planet, and possibly our future. It reminds us that we live on a world with its own complex dynamics, thresholds, and responses to change. Chapter 3. The Dance of Orbit and Ice. To understand why Earth shouldn't have survived the Ice Age cycle, we must first grasp how these remarkable climate oscillations began. The story starts not on Earth, but in space. With the subtle dance of our planet around the Sun, Earth's orbit isn't perfectly circular, but slightly elliptical, and this ellipticity changes over time. Additionally, our planet's axis wobbles like a spinning top, and the orientation of this tilt relative to our orbit shifts gradually over millennia. These three astronomical cycles, changes in orbital eccentricity, axial tilt, and axial precession, combine to create variations in how solar energy is distributed across Earth's surface. Serbian mathematician Milankovitch calculated these effects in the early 20th century. Milankovitch proposed that these orbital variations would affect the intensity of summers in the northern hemisphere, where most continental landmass is located. When northern summers received less solar energy, snow could persist year-round, eventually forming ice sheets. The theory was elegant but presented an immediate problem. The orbital variations changed incoming solar energy by only a tiny fraction, far too little to directly cause the massive climate swings evident in the geological record. Something must have been amplifying these small astronomical nudges into planet-altering climate shifts. This amplification mechanism became the central mystery of paleoclimatology, the study of ancient climates. The first breakthrough came in the 1970s when scientists analyzed deep-sea sediment cores. These oceanic archives contained shells of tiny marine organisms that preserved isotopic signatures of past ocean temperatures and global ice volume. When researchers matched this climate data to Milankovich's orbital calculations, they found remarkable correlation. The Ice Age cycles were indeed paced by orbital variations, confirming Milankovich's basic premise despite the energy shortfall problem. This discovery led to the identification of several feedback mechanisms that could amplify the initial orbital forcing. As ice sheets grew, they reflected more sunlight back to space, cooling Earth further. This ice albedo feedback created a powerful amplification effect. Changes in greenhouse gas concentrations provided another crucial feedback. Ice core data revealed that atmospheric carbon dioxide and methane levels decreased during glacial periods and increased during interglacials, amplifying the temperature changes. Ocean circulation changes added another layer of complexity. The formation and melting of ice sheets affected salinity patterns in the Atlantic Ocean, altering the great conveyor belt of currents that distributes heat globally. But a profound puzzle remained. While Milankovitch cycles occur continuously, the climate record showed a striking shift about 1 million years ago. Before this mid-Pleistocene transition, ice ages followed a 41,000-year cycle matching Earth's axial tilt variations. After the transition, glacial cycles lengthened to approximately 100,000 years, seemingly following Earth's orbital eccentricity cycle. Yet this cycle produces the weakest solar energy variations of all three Milankovitch cycles, making it a puzzling primary driver. This paradox deepened when scientists realized the 100,000-year climate cycle doesn't perfectly match the eccentricity cycle either. The climate system appeared to be following its own rhythm, merely paced by orbital variations rather than directly driven by them. These discoveries revealed Earth's climate as a highly nonlinear system, one where small inputs could produce disproportionately large, and sometimes unpredictable responses. Such systems can exhibit complex behaviors, including threshold effects and self-organization. The emerging picture suggested that Earth's climate might be capable of existing in multiple stable states, with transitions between them triggered by crossing critical thresholds. This raised troubling questions about the inherent stability of our life-supporting climate. If Earth's climate could shift between dramatically different states based on small nudges, what prevented more extreme transitions to permanent icehouse or greenhouse conditions? What invisible guardrails kept the planet within habitable boundaries? Scientists began exploring these questions by developing increasingly sophisticated climate models. These computational tools attempted to recreate the complex interactions between atmosphere, oceans, ice sheets, and the carbon cycle. Early models struggled to reproduce the observed glacial cycles, particularly the 100,000-year periodicity. This failure highlighted gaps in our understanding of Earth's climate machinery and suggested missing feedback mechanisms or thresholds. One provocative hypothesis proposed that ice sheets might be inherently unstable once they reached a certain size. After growing gradually for tens of thousands of years, they could collapse relatively quickly when internal dynamics reached critical thresholds. Another theory suggested the carbon cycle itself contained crucial nonlinearities. Changes in ocean circulation, sea ice, and terrestrial ecosystems might drive carbon dioxide into or out of the atmosphere at different rates depending on the climate state. The geological record offered tantalizing clues. During the depth of glacial periods, atmospheric carbon dioxide levels fell to around 180 parts per million, dangerously close to the minimum threshold required by plants using C3 photosynthesis, which includes most trees. Had CO2 levels dropped much further, large portions of Earth's terrestrial plant life might have faced extinction. This suggests the planet may have approached dangerous thresholds during glacial maxima, only to be pulled back by stabilizing mechanisms. As research progressed, scientists realized they were investigating not just an interesting climate phenomenon, but a fundamental question about Earth's habitability. How had our planet maintained conditions suitable for complex life through these extreme oscillations? The stakes of this question became clearer with the discovery of snowball Earth events in the distant past, episodes when ice extended to low latitudes or possibly covered the entire planet. These events demonstrated that more extreme states were indeed possible. Chapter 4. Messages from the deep past. The quest to understand Earth's improbable climate stability requires evidence. Physical archives preserving the climate story across hundreds of thousands of years. Fortunately, our planet keeps remarkable records locked away in ice, sediment, and stone. Among the most valuable climate archives are ice cores extracted from the ancient ice sheets of Greenland and Antarctica. These cylindrical ice samples contain tiny air bubbles, preserved pockets of ancient atmosphere trapped as snow compressed into ice. When scientists analyze these air bubbles, they can directly measure atmospheric composition from the distant past. The results were startling. Carbon dioxide and methane concentrations oscillated in near-perfect synchrony with temperature through the Ice Age cycles. During warm interglacial periods, CO2 levels reached about 280 parts per million. During the depths of ice ages, they fell to around 180 ppm. This 100 ppm difference represented a massive change in Earth's greenhouse effect and energy balance. But which came first, temperature changes or greenhouse gas changes? This chicken or egg question became central to understanding climate feedbacks. Detailed ice core chronologies revealed that warming typically began slightly before CO2 increases. This finding didn't diminish the greenhouse effect's importance. Rather, it suggested a complex sequence where orbital forcing triggered initial warming, perhaps in specific regions, which then released greenhouse gases that amplified the warming globally. The ice cores revealed another shocking discovery: the abruptness of some climate transitions. In Greenland, temperatures sometimes changed by 10 degrees Celsius or more within decades. These weren't gradual shifts, but sudden lurches from one climate state to another. Such rapid transitions shouldn't be possible in a stable climate system. They suggested the existence of tipping points, thresholds beyond which feedbacks drive the system rapidly toward a new equilibrium state. The ocean floor provided another crucial archive. Marine sediments accumulate slowly but continuously, creating layered records spanning millions of years. Microscopic shells preserved in these sediments carry chemical signatures of past ocean conditions. Analysis of ocean sediment cores confirmed the 41,000-year climate cycle in the early Pleistocene, followed by the transition to the 100,000-year cycle about 1 million years ago. But they also revealed something unexpected about this transition. The shift to longer glacial cycles coincided with gradually decreasing atmospheric CO2 levels over millions of years. This suggested that the climate system's response to orbital forcing might depend on background CO2 levels, a critical insight for understanding stability mechanisms. Furthermore, sediment cores showed that ice age cycles weren't uniform. Each had unique characteristics in timing, intensity, and regional effects. This variability hinted at complex interactions between multiple climate components rather than a simple rhythmic response. Scientists turned to cave formations for additional evidence. Stalactites and stalagmites grow through mineral deposition from dripping water, preserving isotopic signatures of precipitation patterns and temperatures when they formed. These speleothems, as they're called, provided high-resolution climate records from mid-latitude regions, filling gaps between the polar ice cores and tropical ocean sediments. They confirmed that climate changes propagated globally through atmospheric teleconnections. On land, ancient lake beds offered another window into past climates. Lakes expand and contract with changing precipitation, leaving shoreline deposits that mark their historical extent. Their sediments contain pollen that reveals which plant species thrived at different times. These terrestrial records showed that ecosystems didn't simply migrate intact as climate changed. Instead, they disassembled and reassembled in novel configurations as individual species moved at different rates in response to climate shifts. This ecological reshuffling demonstrated life's adaptability, but also revealed vulnerability. Not all species could migrate or adapt quickly enough. The Ice Age cycles drove repeated waves of extinction and speciation, particularly affecting large mammals. Perhaps most intriguingly, fossil and genetic evidence showed that our own species, Homo sapiens, emerged during this period of extreme climate variability. We evolved in Africa around 300,000 years ago, after more than 700,000 years of intensifying glacial cycles. Could our remarkable adaptability as a species, our capacity for innovation, social cooperation, and ecological flexibility be partly a product of evolving during this period of dramatic climate oscillations? Some paleoanthropologists propose exactly this. As evidence accumulated, scientists began constructing increasingly comprehensive models of the Ice Age climate system. These models revealed the central importance of carbon cycle feedbacks in amplifying orbital forcing. During cooling phases, lower ocean temperatures allowed more carbon dioxide to dissolve into seawater, reducing atmospheric concentrations and further cooling the planet. Expanding ice sheets also exposed continental shelves, allowing carbon-rich soils to form. During warming phases, the ocean released dissolved carbon dioxide as its waters warmed. Thawing permafrost and changing vegetation patterns released additional greenhouse gases, creating a powerful amplification effect. But these same feedbacks presented a troubling possibility. If warming released greenhouse gases that caused more warming, what prevented runaway warming? Similarly, if cooling sequestered greenhouse gases and caused more cooling, what prevented runaway glaciation? This question strikes at the heart of the Ice Age paradox. Earth's climate feedbacks should theoretically be capable of driving the planet toward extreme states from which recovery would be difficult or impossible. Yet this never happened. Something must have been maintaining boundaries, invisible guardrails that kept the climate oscillations within a habitable range. The search for these stabilizing mechanisms became a central focus of paleoclimate research. One candidate emerged in the deep ocean circulation system, the global conveyor belt that distributes heat between the equator and poles. Evidence suggested this circulation had different modes of operation during glacial and interglacial periods. When the circulation slowed or partially collapsed during certain climate transitions, it created dramatic regional effects, but also set in motion compensatory processes that may have prevented more extreme global changes. Another stabilizing mechanism appeared to involve the carbon cycle itself. As CO2 levels dropped during glacial periods, plant growth became increasingly carbon-limited, potentially slowing further carbon sequestration and preventing CO2 from falling to life-threatening levels. But perhaps the most provocative hypothesis emerged from considering timescales. The 100,000-year glacial cycle appeared suspiciously close to the lifetime of ice sheets, the period over which they grow until reaching inherent structural or thermal instability. This suggested the Ice Age rhythm might be partially driven by the internal dynamics of ice sheets themselves, their tendency to grow gradually until reaching a critical threshold where rapid collapse becomes inevitable. If true, this would represent a profound insight. Earth's climate stability might depend not just on external astronomical forcing, but on the self-regulating behaviors of its major components, a form of planetary self-organization. As we stand at this point in our understanding, a remarkable possibility emerges. What if Earth's climate stability isn't guaranteed by any single mechanism, but emerges from the complex interactions between multiple systems operating across different timescales? This would transform our understanding of planetary habitability. Rather than seeing Earth as simply lucky to have the right initial conditions, we might recognize it as a dynamically stable system, one that actively maintains its habitability through complex feedback networks. But this perspective comes with a troubling corollary. If Earth's climate stability emerges from the precise configuration of its components and their interactions, how resilient is this stability to significant perturbations? And what happens when humans become one of the most powerful forcing factors in this delicate system? Chapter 5: The Broken Rhythm. As we delve deeper into the Ice Age mystery, contradictions emerge that challenge our understanding. While the Milankovitch cycles elegantly explain the general pattern of glacial-interglacial transitions, detailed examination reveals troubling inconsistencies that shouldn't exist in a well-behaved climate system. The most glaring contradiction is the 100,000-year problem itself. The weakest of the orbital forces, the 100,000-year eccentricity cycle, somehow became the dominant climate pacemaker during the past million years. This defies simple physical explanation. Furthermore, the climate transitions don't perfectly align with orbital parameters. Sometimes ice ages end when orbital forcing is minimal, while at other times, similar orbital configurations produce dramatically different climate responses. This inconsistency suggests Earth's climate system possesses internal dynamics capable of overriding astronomical forcing. It's as if the planet follows orbital cues when convenient, but maintains its own timetable for major climate transitions. Another anomaly appears in the mid-Pleistocene transition, when Earth shifted from 41,000-year to 100,000-year climate cycles about 1 million years ago. This occurred without any corresponding change in orbital dynamics. The heavens continued their clockwork motion unchanged. What could have altered Earth's climate response so fundamentally? Some researchers propose that long-term cooling caused ice sheets to grow thick enough to reach a new stability threshold. Others suggest changes in ocean circulation or greenhouse gas dynamics. But no single explanation has proven entirely satisfactory. The transition remains one of paleoclimatology's most significant unsolved puzzles and raises profound questions about the predictability of Earth's climate system over long timescales. Even more troubling are the abrupt climate changes nested within the larger glacial cycles. Greenland ice cores reveal at least 25 instances of sudden warming events during the last glacial period, where regional temperatures rose 8 to 15 degrees Celsius within decades. These Dansgaard-Oeschger events, as they're called, appear far too rapid to be explained by orbital forcing. They suggest threshold behaviors where the climate system abruptly shifts between alternative states, a deeply concerning property for a supposedly stable system. Heinrich events present another anomaly: periods when massive armadas of icebergs broke from northern ice sheets and floated across the North Atlantic, depositing rock fragments on the ocean floor as they melted. These events dramatically disrupted ocean circulation. The Standard Model struggles to explain why these destabilizations didn't cascade into runaway climate changes. Each Heinrich event represented enormous energy redistribution within Earth's climate system, yet the planet repeatedly recovered its equilibrium. The survival of complex life through these transitions becomes even more remarkable when we consider the carbon cycle anomalies. During glacial periods, atmospheric CO2 fell to levels barely above the survival threshold for C3 photosynthesis used by most plants. Had the carbon sequestration process continued just slightly further, mass extinction of plant life could have occurred. Yet atmospheric CO2 concentrations always stabilized around 180 ppm during glacial maximums, suggesting an unidentified regulatory mechanism. Ocean sediment records reveal another paradox. During the deepest ice ages, the Southern Ocean around Antarctica should have experienced enhanced biological productivity due to iron fertilization from increased dust. This should have sequestered more carbon, creating a runaway cooling effect. Instead, productivity apparently reached a saturation point, preventing further carbon dioxide removal from the atmosphere. Was this merely coincidence or evidence of a previously unrecognized stabilizing feedback within Earth's carbon cycle? Perhaps the most troubling contradiction involves terminations, the relatively rapid transitions from glacial to interglacial conditions. These warming phases occur much faster than the cooling phases, creating a sawtooth pattern in the temperature record. This asymmetry defies simple explanation. Orbital forcing changes gradually, yet the climate system responds with sudden, dramatic warming. Something must be triggering rapid destabilization of ice sheets and release of greenhouse gases at critical thresholds. The timing of terminations presents another anomaly. They often begin when northern hemisphere summer insolation is increasing but still relatively low. If orbital forcing were the primary driver, terminations should align more precisely with peak insolation. This misalignment suggests the ice sheets themselves may be setting the timing. After growing for roughly 100,000 years, they may reach internal instabilities that make them vulnerable to collapse even with modest orbital forcing. A particularly striking contradiction involves Antarctic temperature records. Southern hemisphere warming during terminations sometimes begins slightly before northern hemisphere warming, the opposite of what Milankovitch theory predicts. This bipolar seesaw effect suggests heat redistribution between hemispheres through ocean circulation changes, but it complicates our understanding of what ultimately controls the glacial cycle's timing and progression. When scientists analyze the full sequence of glacial cycles over the past million years, another anomaly emerges. Each cycle has unique characteristics, different durations, intensities, and patterns of change. This irregularity suggests a system influenced by chaotic elements. If Earth's climate contains chaotic components, this raises uncomfortable questions about predictability. How close has the system come to crossing irreversible thresholds? Is the stability we've observed partly a matter of fortunate circumstance rather than robust mechanisms? Greenhouse gas records present yet another puzzle. The correlation between temperature and atmospheric CO2 is remarkably tight over hundreds of thousands of years. But what explains this precise relationship when carbon sources and sinks involve complex biological and geological processes? The carbon cycle shouldn't behave so predictably given its complexity. The consistency suggests unidentified regulatory mechanisms maintaining the carbon-climate relationship through wildly different planetary conditions. Ocean circulation patterns during glacial periods create another contradiction. Evidence suggests the Atlantic meridional overturning circulation, which distributes heat from the tropics to the North Atlantic, operated in a significantly different configuration during ice ages. This altered circulation should have created cascading climate effects, potentially pushing the system toward greater extremes. Yet Earth maintains sufficient stability for complex ecosystems to persist through these major reorganizations of heat distribution. One of the most perplexing anomalies comes from comparing our current interglacial period with previous ones. The Holocene has lasted nearly 12,000 years with remarkable temperature stability. Previous interglacials were often shorter and showed different progression patterns. Is the Holocene's unusual stability merely a fortunate coincidence that allowed human civilization to develop? Or might early human activities, like forest clearing and early agriculture, have inadvertently helped stabilize climate through the last several thousand years? Archaeological evidence offers tantalizing hints. Studies suggest humans may have been altering landscapes and carbon cycles as early as 8,000 years ago. Could these influences have helped prevent the gradual cooling typically seen in previous interglacials? If true, this would be profoundly ironic. Human modifications may have helped maintain stable conditions that enabled civilization to flourish, even as our more recent activities now threaten that same stability. As we confront these contradictions and anomalies, the central mystery deepens. Earth's climate stability through the Ice Age cycles appears increasingly improbable, a delicate balance maintained despite powerful forces that should have pushed the system toward uninhabitable extremes. We're left with a profound question. Is Earth's climate resilience a product of robust, self-regulating mechanisms? Or have we been the beneficiaries of a fortunate series of circumstances that prevented worst-case scenarios from materializing? Chapter 6. Memories in Myth and Stone. While scientific evidence provides our primary window into Earth's climate history, other sources offer intriguing perspectives on how past climate transitions affected human experience. Ancient myths and legends from cultures worldwide contain curious references to dramatic environmental changes. Many indigenous traditions include stories of great floods, extended winters, or times when the sun behaved differently. While these narratives incorporate spiritual and metaphorical elements, they may also preserve memories of actual climate events experienced by ancient peoples. Consider the widespread flood myths. Over 200 different cultures maintain legends of catastrophic deluges that reshaped the world. While no single global flood occurred, the end of the last ice age around 11,700 years ago did cause dramatic sea level rise of about 120 meters. This flooding inundated vast coastal plains where many human populations likely lived. The Persian Gulf, North Sea, and areas between Southeast Asian islands transformed from fertile lowlands to seafloor within human generational memory. Could these traumatic experiences have been preserved in oral traditions, eventually becoming the flood myths we know today? The timing aligns with the catastrophic draining of massive glacial lakes and pulses of sea level rise at the end of the last ice age. Indigenous Arctic peoples maintain traditions describing times when the weather and hunting patterns changed dramatically within a single lifetime. These may preserve cultural memories of the Younger Dryas, a sudden return to near glacial conditions 12,900 years ago. This cold reversal lasted over 1,000 years before warming resumed abruptly. Ice core evidence confirms temperatures in Greenland dropped approximately 15 degrees Celsius within decades. Exactly the kind of dramatic shift that would be seared into cultural memory. Australian Aboriginal traditions include detailed knowledge of coastlines now submerged under 20 to 65 meters of water. Remarkably, geological research confirms these descriptions of ancient shorelines match the actual submerged landscapes, suggesting oral transmission across hundreds of generations. These traditions specifically describe sea level changes, with stories of ancestral hunting grounds becoming gradually submerged. The preservation of such specific geographic knowledge over more than 10,000 years challenges our assumptions about historical memory. North American indigenous traditions describe a time of devastating cold, starvation, and darkness, followed by warming and the disappearance of many large animals. This aligns with the Younger Dryas period and subsequent megafauna extinctions well documented in the fossil record. Beyond myths, archaeological evidence reveals out-of-place findings that challenge conventional climate history. Sophisticated settlements have been discovered in locations that seemed inhospitable during known climate phases, suggesting complex local variations not captured in global models. Göbekli Tepe in Turkey presents one such puzzle. This monumental stone complex was built around 9,600 BCE, during the volatile Younger Dryas period when resources were supposedly scarce. Its construction required organized labor from hunter-gatherer societies not yet practicing agriculture. How could such an ambitious project emerge during a time of climate stress? Some researchers suggest the necessity of adaptation to changing conditions might have driven new forms of social organization and innovation. Underwater archaeology provides another category of anomalous evidence. Submerged settlements have been discovered off coastlines worldwide, confirming human adaptation to landscapes lost during post-glacial sea level rise. These findings include structured stone arrangements 40 meters below the Mediterranean Sea and architectural remains in the Persian Gulf, North Sea, and off India's coast. They reveal human resilience through dramatic environmental transformations. Perhaps most intriguing are climate refugia. regions where local conditions buffered the extremes of global climate changes. Archaeological evidence suggests humans concentrated in these areas during climate downturns, creating hotspots of cultural innovation. The Iberian Peninsula, parts of Southeast Asia, and certain African rift valleys maintained relatively stable microclimates throughout the last glacial maximum. These regions later became centers from which technological and cultural advancements spread. Cave art from the last ice age offers direct glimpses into human experience of climate transitions. European cave paintings from 30,000 to 12,000 years ago predominantly depict animals adapted to cold steppe environments: mammoths, woolly rhinoceroses, and reindeer. As climate warmed, the subject matter shifted to forest species like deer and boar. This artistic record tracks ecosystem changes through human eyes, suggesting acute awareness of environmental transformation among our ancestors. Ancient farming practices reveal another category of anomalous evidence. Some early agricultural settlements show sophisticated adaptation to climate variability, including water management systems far more complex than previously thought necessary for their time. These systems suggest ancient peoples possessed nuanced understanding of climate patterns and their fluctuations. Some researchers propose this knowledge may have included awareness of multi-year climate cycles informed by generations of observation. The abrupt abandonment of flourishing settlements presents another climate-related anomaly. Archaeological evidence shows sophisticated urban centers suddenly deserted despite no signs of warfare or disease, just as regional climate records indicate unexpected drought or cooling. These abandonment events sometimes spread like dominoes across regions, suggesting climate thresholds that, once crossed, made multiple settlements unviable simultaneously. Yet, mysteriously, human populations persisted by migrating or adapting their lifeways. Cultural transitions sometimes appear in archaeological records before detectable climate changes. Some settlements show evidence of preparation for environmental shifts, changing construction methods or food storage systems, seemingly anticipating climate changes modern instruments only recently detected. Could ancient peoples have recognized subtle environmental signals that preceded major transitions? This possibility challenges our assumptions about historical climate awareness and suggests sophisticated ecological knowledge in pre-industrial societies. Human genetic evidence contains its own climate-related anomalies. Population bottlenecks, sharp reductions in genetic diversity, correlate with extreme climate events. Yet these same populations often show subsequent genetic adaptations to cold environments or changing diets. These genetic signatures suggest humans faced strong selection pressure during climate transitions, but demonstrated remarkable adaptability. Our species' genetic resilience through climate extremes may offer insight into our evolutionary relationship with environmental change. Ancient agricultural practices reveal climate adaptation strategies seemingly ahead of their time. Terracing, water harvesting systems, and polyculture approaches often emerged during periods of climate instability, suggesting innovation driven by environmental pressure. Some of these techniques maintained productivity through climate variations that modern single-crop agriculture would find devastating. This hints at sophisticated climate knowledge embedded within traditional agricultural practices developed during past climate transitions. The distribution of early human migration routes presents another anomaly. These pathways often follow corridors that would have had moderate microclimates during climate extremes, suggesting detailed environmental knowledge guiding human movement. These migration patterns indicate that early humans weren't simply fleeing environmental degradation, but strategically navigating a changing climate landscape, perhaps following predictable resources through shifting ecosystems. The preservation of biological knowledge in traditional pharmacopoeias represents another form of climate adaptation memory. Indigenous medical traditions worldwide include plants used to treat conditions specifically associated with climate transitions, respiratory ailments during cold periods, or waterborne diseases during floods. This specialized knowledge suggests multi-generational adaptation to cyclical climate challenges, with cultural practices evolving to address predictable health impacts of environmental changes. When we integrate these diverse lines of evidence, myths, archaeology, genetics, and traditional knowledge, a compelling picture emerges of human experience through climate transitions. Our ancestors weren't passive victims of environmental change, but active adapters with evolving strategies. This realization transforms our understanding of humanity's relationship with climate instability. Rather than being separate from Earth's climate story, humans appear to be embedded within it, both shaped by climate transitions and increasingly capable of shaping them. Chapter 7. The precipice of understanding. As we assemble the puzzle pieces of Earth's climate history, the stakes of our investigation grow increasingly apparent. What began as scientific curiosity about ice age cycles has evolved into a profound inquiry about planetary habitability and humanity's place within Earth's systems. The evidence challenges our fundamental assumptions about climate stability. Earth's climate doesn't merely fluctuate within safe boundaries. It approaches dangerous thresholds, reorganizes major systems, and experiences abrupt transitions that should, theoretically, spiral toward uninhabitable extremes. Yet life persisted. Complex ecosystems survived. Our own species emerged and flourished during this period of dramatic climate oscillations. This remarkable resilience demands explanation and carries implications far beyond academic interest. If Earth's climate stability through the ice age cycles was highly improbable, perhaps even requiring specific combinations of feedback mechanisms unique to our planet, this dramatically affects our understanding of habitable worlds throughout the universe. Consider the implications for astrobiology. If maintaining conditions suitable for complex life requires not just the right initial conditions, but also precise feedback systems to regulate climate through astronomical forcing cycles, the number of potentially life-supporting planets may be far smaller than currently estimated. Most exoplanet habitability models focus on the Goldilocks zone, where liquid water can exist. But our investigation suggests a deeper requirement: internal regulatory mechanisms capable of maintaining stability despite external perturbations similar to Milankovitch cycles. Every star system experiences orbital variations. If planets lack robust, self-regulating climate systems, these astronomical cycles could easily push their environments beyond habitable boundaries. Earth's resilience might be exceptional rather than typical. This perspective transforms the Fermi paradox, the contradiction between high probability estimates for extraterrestrial intelligence and the lack of contact or evidence. Perhaps complex life is rare precisely because climate self-regulation through orbital cycles is uncommon. The stakes extend to our understanding of Earth's future. If our planet's climate stability has depended on specific configurations of ice sheets, ocean currents, and carbon cycle dynamics, how resilient is this system to human-induced changes occurring at unprecedented rates? We now understand that Earth's climate system contains tipping points, thresholds beyond which abrupt, nonlinear changes occur. The Ice Age record reveals multiple instances where such tipping points were approached, but somehow not crossed irreversibly. What prevented catastrophic runaway effects? Were there inherent stabilizing mechanisms, or did Earth simply remain fortunate through hundreds of close calls? The answer carries profound implications for our climate future. If robust, self-regulating mechanisms exist, they might help buffer human-caused climate change. Conversely, if past stability partially reflected fortunate circumstances, we may be undermining resilience that took millions of years to develop. The stakes escalate further when we consider that human civilization developed entirely within the Holocene, an interglacial period of unusual climate stability compared to the preceding 100,000 years. Our agriculture, settlements, and infrastructure evolved under these stable conditions. Archaeological and geological evidence suggests the Holocene might have naturally been ending toward a new glacial period, with slight cooling trends observed prior to the Industrial Revolution. Human activities have potentially both prevented this cooling and now driven warming at rates unprecedented in the Ice Age cycles. This places humanity in an extraordinary position. We have become a climate-forcing factor comparable to orbital variations in power, but operating at vastly greater speed. We are effectively short-circuiting natural climate cycles that previously unfolded over tens of thousands of years. Understanding Earth's resilience through past climate transitions becomes critical for navigating our future. Did previous stability depend on conditions we've now altered? Or might the same mechanisms that prevented runaway effects during glacial cycles help moderate human impacts? The stakes extend to our fundamental relationship with Earth systems. The conventional view portrays nature as fundamentally stable until disrupted by human activities. The Ice Age record reveals a more nuanced reality. Earth's environment has always been dynamic, with or without human influence. This recognition transforms environmental ethics. Rather than simply leaving nature alone, humanity's challenge becomes understanding how to participate in Earth's systems without undermining the regulatory mechanisms that maintained habitability through extreme climate transitions. Research into ancient climate transitions has revealed that ecosystems don't simply migrate intact as conditions change. They disassemble and reassemble in novel configurations as species move or adapt at different rates. This process created unprecedented ecological communities during previous transitions. Today's climate change is occurring 10 to 100 times faster than most natural transitions, potentially outpacing adaptation for many species. Yet the Ice Age record suggests some ecosystems and species displayed remarkable resilience through repeated, dramatic climate oscillations. What made some biological systems more resilient than others? The paleoclimate record shows certain ecological configurations maintained functionality despite composition changes. Understanding these resilience factors could inform conservation strategies for our warming world. The human story within climate transitions carries its own escalating stakes. Genetic and archaeological evidence suggests climate volatility may have driven human innovation, social complexity, and technological development, selecting for the very traits that define our species. If climate variability shaped human evolution and cultural development, this transforms our understanding of our relationship with environmental change. Rather than being foreign to our nature, adapting to climate shifts may be central to our evolutionary and cultural story. Yet today's changes differ critically from those that shaped our species. Modern climate change occurs in a world of fixed national boundaries, immobile infrastructure, and specialized agricultural systems, constraints that didn't exist for most of human evolution. Our adaptability now depends less on genetic or physiological flexibility and more on social, technological, and governance innovations. The question becomes whether our cultural evolution can match the pace of our environmental impact. Perhaps the highest stakes involve our conception of planetary habitability itself. The traditional view defines habitable zones based on relatively simple parameters: temperature ranges permitting liquid water and basic chemistry supporting life. The Ice Age investigation reveals a more complex reality. Earth maintained habitability not through static conditions, but through dynamic self-regulation, complex feedback systems that prevented transitions to uninhabitable states despite powerful destabilizing forces. This perspective aligns with the Gaia hypothesis proposed by James Lovelock and Lynn Margulis, the concept that life itself participates in regulating planetary conditions favorable to its continued existence. The Ice Age cycles provide the most stringent test case for this controversial idea. Did life-climate feedbacks help prevent extreme outcomes during glacial cycles? Evidence suggests biological processes influenced atmospheric composition, surface reflectivity, weathering rates, and ocean chemistry in ways that moderated climate swings. If life has been an active participant in maintaining Earth's habitability through extreme climate transitions, this fundamentally changes our understanding of the relationship between planets and their biospheres. Habitability may emerge from biological planetary coevolution rather than existing as a precondition. This coevolutionary perspective dramatically escalates the stakes of biodiversity loss. If Earth's climate resilience partly depends on biological diversity and functional ecosystems, then biodiversity isn't merely something to preserve for aesthetic or moral reasons, but essential planetary life support. As our investigation approaches its climax, we face the most profound questions. Was Earth's survival through the Ice Age cycles a product of robust, self-regulating systems? Or have we been the beneficiaries of a fortunate series of circumstances that repeatedly prevented worst-case outcomes? The answer has extraordinary implications for humanity's future. If Earth possesses inherent resilience through negative feedback mechanisms, these same systems might help buffer human impacts. If past stability depended partly on specific conditions we're now altering, we may be undermining the very foundations of planetary habitability. Perhaps most provocatively, we must consider whether humanity itself now constitutes a significant component of Earth's regulatory systems. Having evolved within this dynamic planetary system, we've become its most powerful modifying force, capable of both destabilizing and potentially enhancing resilience. Our growing understanding of Ice Age climate dynamics has revealed a planet poised between stability and chaos, a complex system that maintained conditions for complex life despite repeated approaches to potential points of no return. The central mystery deepens. What invisible guardrails kept Earth's climate oscillations within habitable boundaries? And as we identify these critical regulatory mechanisms, are we inadvertently dismantling them through our unprecedented impacts on the atmosphere, oceans, and biosphere? As we prepare to address these questions, we stand at a unique moment in Earth's history, the first time a species has developed sufficient understanding to comprehend the planet's climate history and sufficient power to rival natural forcing factors in shaping its future. Chapter 8. The Great Regulatory Mechanisms. As we approach the climax of our investigation, we must consider the competing theories that might explain Earth's improbable climate stability. Three primary hypotheses have emerged, each with compelling evidence, but also significant limitations. The first hypothesis proposes that Earth's climate stability through Ice Age cycles resulted primarily from carbon cycle feedbacks, natural processes that regulate atmospheric greenhouse gas concentrations in response to temperature changes. According to this theory, as Earth began cooling due to orbital variations, the oceans absorbed more carbon dioxide, enhancing cooling. Eventually, reduced plant productivity in colder conditions limited further carbon sequestration, preventing runaway glaciation. Similarly, during warming phases, the oceans released dissolved carbon dioxide, enhancing warming. But increased plant growth and silicate weathering eventually removed carbon dioxide from the atmosphere, preventing runaway greenhouse conditions. Evidence for this hypothesis comes from the remarkably tight correlation between temperature and atmospheric carbon dioxide levels throughout the Ice Age record. The relationship is so consistent that the two appear mechanistically linked through multiple feedback systems. Additionally, lab experiments have confirmed the temperature dependence of carbon dioxide solubility in seawater, while geological evidence demonstrates how weathering rates respond to temperature and carbon dioxide levels, creating a long-term thermostat effect. However, this theory struggles to explain the mid-Pleistocene transition from 41,000-year to 100,000-year climate cycles. If carbon feedbacks were the primary regulatory mechanism, why did their characteristic response time apparently change about 1 million years ago? The second major hypothesis focuses on ice sheet dynamics. This theory suggests that ice sheets themselves contain inherent constraints on their growth and stability, preventing them from expanding beyond certain limits or persisting indefinitely. According to this view, ice sheets grow gradually during cooling phases until they become unstable through internal dynamics. These instabilities might include basal melting, as thickening ice insulates its base from cold surface temperatures, or physical constraints from topography. Once ice sheets reach critical thresholds, they become vulnerable to relatively small orbital forcing changes, explaining why deglaciations often begin before maximum orbital forcing occurs. This built-in instability prevented permanent glaciation of the planet. Evidence for the ice sheet hypothesis comes from the sawtooth pattern of glacial cycles, slow cooling followed by relatively rapid warming. This asymmetry suggests internal ice sheet dynamics rather than simple response to the more sinusoidal orbital forcing. Geological evidence also reveals how ice sheets physically altered their environments in ways that affected their own stability. They depressed the Earth's crust beneath them, changing regional elevations. They also modified atmospheric circulation patterns around their massive heights. Computer models suggest ice sheets reaching certain thicknesses would experience inevitable basal melting regardless of surface temperatures. This mechanism could explain why ice sheets consistently collapsed after reaching specific volumes, preventing permanent glaciation. However, this hypothesis struggles to explain why deglaciations became synchronized globally. If internal ice sheet dynamics were the primary control, we might expect more regional variation in the timing of glacial terminations than the record actually shows. The third major hypothesis, and perhaps the most provocative, proposes that biological processes played a crucial regulatory role. This theory suggests Earth's biosphere actively participated in climate regulation through multiple feedback mechanisms. In this view, ecosystems adapted to climate changes in ways that moderated further change. During glacial advances, forests retreated and tundra expanded, changing surface reflectivity. Marine ecosystems altered carbon sequestration rates in response to changing conditions. These biotic responses weren't merely passive adaptation, but created feedback effects that influenced climate trajectories. The theory suggests life and climate co-evolved regulatory relationships that maintained conditions within habitable boundaries. Evidence for biological regulation includes the remarkable consistency of minimum carbon dioxide levels during glacial periods, approximately 180 ppm, just above the threshold where widespread plant death would occur and potentially release massive carbon stores. Marine sediment records show changes in oceanic biological productivity synchronized with climate transitions. Shifts in plankton communities affected carbon sequestration rates, while terrestrial ecosystem changes influenced albedo, weathering rates, and soil carbon storage. Genetic evidence reveals many species underwent adaptive radiation during climate transitions, potentially enhancing ecosystem resilience to climate extremes. This biological innovation may have been crucial for maintaining functional ecosystems through dramatic environmental changes. However, critics note that biological regulation should logically become more effective over evolutionary time. Yet Earth has experienced increasingly dramatic climate oscillations during the past million years, the opposite of what improved biological regulation would predict. Each of these hypotheses, carbon cycle feedback, ice sheet dynamics, and biological regulation, explains certain aspects of Earth's climate resilience, but struggles with others. The most compelling current understanding integrates elements from all three. Modern scientific consensus suggests Earth's climate resilience through glacial cycles likely emerged from interactions between these mechanisms operating across different timescales, a nested set of feedback systems that collectively prevented transitions to uninhabitable states. Carbon cycle feedbacks provided regulation across millennial timescales, while ice sheet dynamics influenced centennial-scale responses. Biological adaptations operated across even shorter intervals, with some ecosystem responses occurring within decades. This integrated perspective helps explain why Earth's climate system has proven both variable and resilient, capable of dramatic transitions while maintaining long-term habitability. The multiple regulatory mechanisms created redundancy, preventing any single failure from causing catastrophic outcomes. However, this integration raises a troubling possibility. If Earth's climate resilience depended on the precise configuration of these interconnected systems, human activities may be simultaneously disrupting multiple regulatory mechanisms for the first time in planetary history. We've altered the carbon cycle by adding greenhouse gases at rates far exceeding natural processes. We've drastically modified Earth's surface through deforestation and agriculture, changing albedo and water cycles. We've reduced biodiversity, potentially undermining biological regulatory capacity. Are we disabling the very mechanisms that maintained Earth's habitability through previous climate challenges? This question brings us to the frontier of scientific understanding and the highest stakes of our investigation. What appears increasingly clear is that Earth's climate stability was neither an accident nor guaranteed. It emerged from complex interactions between astronomical, geological, chemical, and biological processes, a dynamic balance rather than a static state. This understanding transforms our perception of planetary habitability. Rather than seeing Earth as simply well-positioned around its star, we recognize it as a dynamic system that actively maintained its habitability through astronomical challenges that could have rendered it uninhabitable. As we prepare to examine cutting-edge research that may resolve these competing hypotheses, one profound insight already emerges. Earth's climate history reveals not a planet fortunate enough to remain habitable by chance, but one that repeatedly averted potential catastrophes through multiple regulatory systems. Chapter 9: Breakthroughs and Paradoxes. Recent scientific advances have transformed our understanding of Ice Age dynamics, revealing complexities that both clarify and deepen the central mystery of Earth's resilience. New analytical techniques, high-resolution climate records, and sophisticated computer models have generated breakthrough insights alongside perplexing new paradoxes. Perhaps the most significant advancement comes from improved ice core chronologies. By synchronizing ice records with precisely dated cave formations and lake sediments, scientists have constructed climate timelines accurate to within decades across hundreds of thousands of years. This enhanced precision revealed something surprising. Major climate transitions often propagated from specific geographic origins rather than changing synchronously worldwide. Many terminations appear to have begun in the North Atlantic before spreading globally through atmospheric and oceanic teleconnections. This regional initiation pattern suggests localized tipping points triggered broader climate reorganization, a finding that challenges simple models of orbital forcing while highlighting the importance of Earth's internal dynamics in climate regulation. Another breakthrough comes from sediment cores revealing ancient ocean circulation patterns. New chemical tracers and isotope techniques have mapped past movements of deep ocean currents with unprecedented detail, showing dramatic reconfigurations during climate transitions. These records confirm that the Atlantic meridional overturning circulation, the current system that distributes heat between the equator and North Atlantic, repeatedly collapsed and re-established during glacial cycles. Each reorganization triggered cascading climate effects across hemispheres. Remarkably, these circulation changes appear to have created compensatory effects. When heat transport to the North Atlantic diminished, Southern Hemisphere warming often increased. This hemispheric seesaw may have prevented either pole from experiencing extreme cooling or warming. Could this oceanic balancing act represent one of Earth's critical regulatory mechanisms? If circulation changes in one region triggered compensatory responses elsewhere, this might explain how the planet maintained overall energy balance despite dramatic regional changes. Advances in paleobotany have revealed another potential regulatory mechanism. New techniques for analyzing ancient pollen, plant fossils, and molecular biomarkers have reconstructed ecosystem responses to climate changes with unprecedented detail. These records show vegetation transitions weren't simply passive responses to changing temperatures. Plant communities actively modified local conditions through changes in evapotranspiration, surface reflectivity, soil development, and carbon storage. Intriguingly, these biological responses often created negative feedbacks that moderated further climate change. When warming began, expanding forests absorbed carbon and darkened landscapes, enhancing warming. But they also increased cloud-forming evapotranspiration, creating cooling effects. This balance of positive and negative biological feedbacks may have been crucial for preventing runaway climate effects. The biosphere appears to have functioned as a dynamic buffer, absorbing some climate changes while amplifying others in complex patterns. Perhaps the most profound scientific advancement comes from our ability to reconstruct past greenhouse gas concentrations with precision down to parts per billion. These high-resolution records reveal subtle features previously hidden in the climate story. One striking discovery is that atmospheric methane concentrations often changed before carbon dioxide during climate transitions. Since methane has powerful greenhouse effects but relatively short atmospheric lifetime, these early shifts may have helped initiate climate transitions. Wetlands, permafrost, and potentially methane hydrates in ocean sediments all released or absorbed methane in response to initial climate nudges. These rapid methane feedbacks may have provided the amplification necessary to overcome climate system inertia. This finding suggests a potential explanation for how small orbital forcing could trigger larger climate responses. Initial forcing may have activated sensitive methane feedbacks, which then initiated broader carbon cycle responses that sustained larger climate transitions. Advanced climate modeling has revealed another crucial insight. When models incorporate realistic ice sheet dynamics, ocean circulation changes, and carbon cycle feedbacks, they generate emergent behavior, complex patterns not programmed into the models, but arising from interactions between components. Some models spontaneously produce the 100,000-year climate cycle from interactions between components, even without strong orbital forcing at that frequency. This suggests the cycle might be partially an internal rhythm of the Earth system rather than purely astronomically driven. If Earth's climate possesses internal rhythms shaped by the characteristic timescales of its components, This would explain why climate transitions sometimes appear out of sync with orbital forcing. The system follows its own tempo while still being paced by astronomical influences. Another breakthrough comes from ancient DNA analysis of Ice Age organisms. By extracting genetic material from fossils, scientists can track evolutionary responses to climate change, revealing how species adapted to extreme environmental transitions. These genetic records show that many species underwent accelerated evolution during major climate transitions. Populations that survived often exhibited genetic changes related to cold tolerance, dietary flexibility, or reproductive timing, adaptations that enhanced resilience. This accelerated evolution during climate transitions suggests biological adaptation may have been another crucial regulatory mechanism. As environments changed, selective pressure favored organisms that could maintain ecosystem functions under new conditions. The most perplexing paradox emerging from recent research involves carbon dioxide levels during glacial periods. New measurements show these concentrations were remarkably consistent across multiple ice ages, stabilizing around 180 to 190 ppm regardless of ice age intensity or duration. This consistency defies simple explanation. If carbon sequestration continued throughout glacial periods, CO2 levels should have continued declining. Something must have prevented further carbon dioxide removal despite continuing cold conditions that favored oceanic absorption. One hypothesis suggests that when CO2 approached this lower limit, marine productivity declined sufficiently to reduce further carbon sequestration. Alternatively, exposed continental shelves during low sea levels may have released carbon that offset continued oceanic absorption. Whatever the mechanism, this CO2 floor appears to have been a critical safeguard preventing runaway glaciation. Had carbon dioxide levels fallen much lower, global photosynthesis would have been severely compromised, potentially triggering ecosystem collapse and climate destabilization. Another paradox involves the interglacial periods themselves. Recent research shows these warm intervals weren't identical but varied in temperature, duration, and climate patterns. Some were warmer than others, some briefer, some with different rainfall distributions. This variation challenges simplistic orbital explanations. If interglacials were purely responses to similar orbital configurations, they should have been more consistent. Their diversity suggests internal Earth system dynamics substantially influence their expression. Perhaps the most significant recent advancement comes from refined understanding of climate sensitivity, how much warming results from a given increase in greenhouse gases. Paleoclimate records suggest Earth's long-term sensitivity exceeds estimates based solely on physical processes. This higher sensitivity likely reflects slow feedbacks not captured in short-term measurements, changes in vegetation, ice sheets, and carbon cycle dynamics that unfold over centuries to millennia. These long-term responses amplified initial climate forcings throughout the Ice Age cycles. The recognition of these slow feedbacks creates a troubling paradox for our current situation. If Earth's climate is more sensitive to greenhouse gas changes over long time frames, the full warming from current emissions may unfold over centuries, even if emissions stop immediately. As we assimilate these scientific breakthroughs, a remarkable picture emerges of Earth as a complex adaptive system, one whose stability emerges from interactions between components rather than from any single regulatory mechanism. This perspective transforms our understanding of planetary resilience. Earth maintained habitability not by resisting change, but by changing in ways that prevented transitions to uninhabitable states. Its resilience lay in dynamic response rather than static conditions. This dynamism extended across multiple timescales and systems, from rapid atmospheric adjustments to gradual ice sheet evolution and slower still crustal responses. Each provided distinct regulatory mechanisms operating in concert to maintain overall habitability. As we stand at the frontier of this understanding, preparing to synthesize what we've learned into a coherent explanation for Earth's survival through the Ice Age cycles, one insight stands paramount. Earth's habitability was actively maintained rather than passively preserved. Chapter 10. The Rhythm of Resilience. We've arrived at the culmination of our investigation, the moment to address our central question. Why did Earth maintain habitable conditions through Ice Age cycles that, by reasonable scientific expectations, should have pushed the climate system toward uninhabitable extremes? The answer, emerging from converging lines of evidence, reveals a profound truth about our planet. Earth survived because it functions as a complex adaptive system with multiple, overlapping regulatory mechanisms operating across different timescales and components. This isn't a simple or singular explanation. Earth's resilience didn't derive from any one feedback mechanism, but from a nested hierarchy of processes that collectively prevented the climate system from crossing irreversible thresholds despite powerful destabilizing forces. What scientists have discovered is that our planet maintained habitability through ice age cycles because four critical regulatory systems operated in tandem, each providing distinct stabilizing influences when the others approached their limits. The first regulatory system involves the physical dynamics of ice sheets themselves. Research has confirmed that ice sheets contain inherent growth limitations. As they thicken, their bases experience increased pressure and insulation from surface temperatures, eventually causing basal melting. This internal constraint prevented ice sheets from growing indefinitely despite continued cold conditions. When they reached critical thicknesses, typically after about 100,000 years of growth, they became inherently unstable and vulnerable to collapse even with modest orbital forcing. The second regulatory system operated through ocean circulation patterns. When cooling threatened to become extreme, changes in freshwater distribution from growing ice sheets altered ocean circulation in ways that often redistributed heat rather than allowing unlimited cooling. When the Atlantic meridional overturning circulation weakened during glacial periods, it reduced heat transport to the North Atlantic but often increased warming in southern regions. This hemispherical seesaw effect prevented either pole from experiencing runaway cooling. The third crucial regulatory system involved carbon cycle feedbacks that maintained greenhouse gas concentrations within habitable bounds. When cooling intensified, decreased terrestrial vegetation reduced carbon dioxide removal, while ocean stratification reduced marine carbon sequestration. These negative feedbacks prevented atmospheric carbon dioxide from falling below approximately 180 ppm during glacial maximums, just above the threshold where widespread plant death would occur and potentially trigger ecosystem collapse. During warming phases, increased weathering of exposed silicate rocks gradually removed carbon dioxide, while expanding forests sequestered additional carbon. These processes slowed warming and eventually helped initiate cooling phases, preventing runaway greenhouse conditions. The fourth and perhaps most remarkable regulatory system involved biological adaptation and ecosystem resilience. As climate conditions changed, species migrated, adapted, or were replaced by others that maintained critical ecosystem functions under new conditions. This biological reorganization preserved fundamental processes like primary productivity, nutrient cycling, and carbon sequestration despite changing species compositions. The biosphere maintained functional continuity through dramatic environmental transformations. What makes Earth's survival through ice age cycles truly remarkable is how these regulatory systems operated across different timescales, creating redundancy that prevented any single failure from causing catastrophic outcomes. Physical ice sheet constraints operated over millennial timescales. Ocean circulation changes occurred over centuries to millennia. Carbon cycle feedbacks range from decades to thousands of years. Biological responses span generations to evolutionary timescales. This temporal distribution of regulatory mechanisms meant that when one system approached its limits, others could compensate. If carbon cycle feedbacks weakened, ice sheet dynamics or ocean circulation changes could provide alternative stabilizing influences. The revelation that emerges from modern climate science isn't that Earth got lucky through hundreds of close calls, but that our planet developed robust, self-regulating characteristics that maintained habitability despite dramatic climate forcing. This understanding transforms our conception of what makes a planet habitable. It isn't merely the right distance from a star or the presence of water, but the development of integrated regulatory systems that maintain suitable conditions despite external perturbations. Perhaps most profoundly, we now recognize that Earth's climate resilience emerges from the entire Earth system. The integrated functioning of atmosphere, hydrosphere, cryosphere, lithosphere, and biosphere operating as a coupled network of influence and response. This perspective aligns with the Gaia hypothesis, but with important scientific refinements. Earth's self-regulation isn't goal-directed or conscious, but emerges from physical, chemical, and biological processes that, through natural selection and feedback dynamics, created stabilizing patterns. Life plays a crucial role in this regulation, not through intentional action, but because organisms that modified their environments in ways that promoted their continued existence were more likely to persist through climate transitions. This created effective planetary regulation. The implications of this understanding extend far beyond scientific curiosity. If Earth's habitability depends on complex regulatory networks rather than simply favorable initial conditions, this dramatically affects how we perceive both our own planet's resilience and the potential for life elsewhere. For our future, it suggests that maintaining Earth's habitability requires preserving the integrity of these regulatory systems. The carbon cycle, ocean circulation patterns, ice sheet dynamics, and biological diversity that collectively enabled our planet to weather astronomical challenges. Human activities are now affecting all four major regulatory systems simultaneously, altering the carbon cycle through emissions, changing ocean circulation through warming and freshwater inputs, accelerating ice sheet dynamics, and reducing biological diversity and resilience. We're essentially conducting an uncontrolled experiment with the very systems that maintained Earth's habitability through previous climate challenges. Understanding these regulatory mechanisms becomes essential for responsible planetary stewardship. For astrobiology, our discoveries suggest habitable planets may be rarer than previously estimated. True habitability may require not just the right initial conditions, but the development of robust regulatory systems capable of maintaining stability through astronomical forcing cycles. The search for extraterrestrial life perhaps should focus not just on planets in the traditional habitable zone, but on those showing evidence of long-term climate stability despite orbital variations, signs of the regulatory processes that made Earth's complex life possible. Our journey through Earth's ice age cycles reveals a profound truth. Our planet isn't merely a stage upon which life's drama unfolds, but an integrated system where geological, chemical, and biological processes create the conditions that allow complex life to flourish. Earth shouldn't have survived the ice age cycles if it were merely a rock with water orbiting a star. It survived because it evolved into a complex system with emergent regulatory properties. A remarkable planet that maintained its habitability not through luck, but through the integrated functioning of its components. As we contemplate our place within this system, we gain a deeper appreciation for both Earth's resilience and its vulnerability. The regulatory mechanisms that preserved habitability through astronomical challenges now face disruption at rates unprecedented in Earth's long history. Understanding how our planet maintains stability through past climate extremes provides our best guide for preserving habitability into the future. Earth's great climate cycles reveal not just where we came from, but how we might ensure our planet remains hospitable for generations to come. As our exploration of Earth's improbable climate resilience concludes, we're left with both answers and deeper questions. We've discovered that our planet maintained habitability through ice age cycles not by chance, but through integrated regulatory systems operating across different components and timescales. Yet this understanding opens new horizons of inquiry. If Earth's climate resilience emerges from complex system dynamics rather than simple physical properties, how fragile or robust is this resilience to novel perturbations? Are there thresholds beyond which recovery becomes impossible? The Ice Age story reveals Earth as neither eternally stable nor chaotically unpredictable, but as a dynamically resilient system capable of maintaining habitability through dramatic transitions. This perspective transforms how we understand both our planet's past and its possible futures. For centuries, humans perceived Earth as either unchanging or subject to catastrophic disruptions. The Ice Age cycles reveal a more nuanced reality. A planet that changes constantly, yet maintains continuity, that experiences dramatic transitions, yet preserves the conditions for complex life. Perhaps the most profound insight from our journey is that humanity now constitutes a significant component of Earth's regulatory systems. Having evolved within this dynamic planetary system, we've become a geological force capable of both undermining and potentially enhancing resilience. As we face the climate challenges of our century, The Ice Age cycles offer both warning and hope. They warn of the system's capacity for rapid, nonlinear transitions when critical thresholds are crossed. Yet they also testify to Earth's remarkable ability to maintain habitability through extreme conditions. Our species emerged during this period of climate volatility, with our remarkable adaptability likely shaped by these environmental challenges. Now we must apply our unique capacities for foresight, cooperation, and innovation to preserve the planetary systems that made our existence possible. The rhythm of ice and time continues, a planetary pulse that has beaten for millions of years. As temporary inhabitants of this ancient Earth, we've been granted a glimpse into its remarkable history and the opportunity to ensure its continued hospitability for all that will follow. If you found this journey through Earth's climate history fascinating, consider subscribing to our channel for more explorations of our planet's profound mysteries. Together, we'll continue unraveling the remarkable story of our home in the cosmos, this improbable, resilient, ever-changing Earth.